Hello, everyone. Welcome to AIUK's session on machine learning for finance. I'm your host, Adriano Koshiyama, Research Fellow at UCL Computer Science Department and founder of Holistic AI. Most of my previous doctoral research, partially done at the Turing Institute, was centered in the intersection of machine learning and finance, particularly on GANs and transfer learning. So I'm really excited to participate in this session and chair this upcoming debate. So today's session on machine learning for finance will feature three experts in the topic. The first speaker, Dr. Lucas Pruch, Director of Finance and Economics at the Turing Institute, will talk about synthetic data generation. Our second speaker, Professor Steve Roberts, Royal Academy of Engineering and MEM Group Professor of Machine Learning at University of Oxford, will speak about the challenges and opportunities of using AI and ML for finance. And finally, Dr. Weishak Pell, Chancellor's Fellow and Faculty at the School of Informatics at University of Edinburgh, will share insights on principles and practice of explainable machine learning. Before I formally open the floor for the first speaker, I just want to do some housekeeping. First, feel free to ask questions using the Slido, and by the end of the three talks, we will aim to answer as many as possible. Second, please share the key insights from our session through your Twitter and other social media using the hashtag AIUK. So let me introduce the first speaker. Lucas Pruch is a reader, associate professor, as in the America would say, at the School of Mathematics, University of Edinburgh. He's also a Turing Fellow at the Alan Turing Institute, London. Before moving to Edinburgh, he was a Nomura Junior Research Fellow at the Institute of Mathematics, University of Oxford, and a member of the Oxford Mann Institute for Quantitative Finance. So the floor is yours. Take it from there, Lucas.
Thank you, Adriano. Thanks a lot. Welcome everyone to the session Machine Learning in Finance. So I want to tell you today about synthetic data generation and synthetic data. That's a topic that is quite exciting, as lots of people at the moment are excited about this. We could heard some comments on that yesterday from Fernando Lucchini from Accenture and Louisa Nolan from ONS. So there's a lot of buzz behind it. So I'd like to present the key ideas, what synthetic data generations are, what they're good for, and maybe what they're not so good for. So the key motivation behind it, or initial motivation at least, is around privacy. So we all know that sharing data is a major roadblock for innovation. We have all, especially in academia, really exciting ideas how we could innovate, introduce fancy, sophisticated data science techniques to extract information out of data. However, it's not so easy to actually get access to data, especially when working within highly regulated industries such as finance and health. So there are these roadblocks, there are challenges, and there is plenty of different solutions. You know, there is a really exciting research, a lot of that done actually at the Turing around privacy enhancing technologies. There are safe havens that allow some access to data to the external researchers. However, those solutions, especially those safe havens, it still takes time to get a permission to get access to data. Even if that access to data is granted, it's not always possible to publish and release outcomes of analysis due to privacy constraints. And those technologies might be expensive to maintain and limit external collaboration. So the idea that we are working on a lot at the moment at the Turing is around synthetic data. So this is about producing and synthetic samples of the data sets that match statistical properties of original data set. We might be interested in fitting all statistical properties or some selected statistical properties of selected features that are relevant for the machine learning or data science task that we have at hand. So those synthetic data can be generated by using some calibrated statistical or econometric models, and people have been working on that, since 70s. However, recent advances in machine learning, and in particular methods such as generative adversarial networks or variational encoders, showed us that it is possible to really do a good job in synthesizing, in producing a good quality, high fidelity synthetic data samples in challenging high dimensional cases. The good synthetic generators are not only trying to capture the relevant statistical properties, but we might also be interested in capturing relevant structural properties, for example, in the case where we might be working with a network data or time series. So why the excitement around that topic? Synthetic data provides additional tool in the rich toolbox of privacy-enhancing technologies. And while classically privacy-enhancing technologies are working on one-to-one de-identification of original data by adding some perturbation, noise, and various obfuscation techniques, the synthetic data is a little bit different. It's producing independent data set based on real data set, and therefore this one-to-one correspondence it's not there, and therefore there is a hope that those methods will work better. So they really, the reason that people are excited about this is that as we're trying to obfuscate original data using classical methods, i.e. by adding, like I said, more noise, then typically the utility and the value of that data is going down. We do too much perturbation, we change the data too much for it to be useful. On the other hand, when using synthetic data, the basic idea is, like I said, you could use any econometric models or agent-based models to simulate data that is similar, but you can also calibrate it and improve the trade-off on this utility privacy between utility and privacy of that data. So that's where the hope is, and these methods can be combined with other privacy-enhancing technologies, and that's why there are lots of promises behind it. So why use synthetic data? So like I said, it's a tool. The key application for it is not to replace original data, but enable a rapid prototyping and development on machine learning in the situation where often we are in a kind of a chicken and egg problem. We don't have access to data, and we say, well, if we had access to data, we could demonstrate the value of it. And so there is this a roadblock, and here being able to demonstrate the value on the data on a synthetic sample before getting access to original data set can be extremely valuable and really can hugely accelerate the development of the projects. This applies to, of course, academia, where academics and PhD students would like to get access to data sets to be able to demonstrate the value of academic research, but also these ideas apply to data sets that are siloed with an organization where different departments have different access to different data sets, and really those data science projects and developments are taking a lot of time. Having good synthetic data generations, good models for the data, can also help to provide additional information about the data, can be used to detect some anomalies in the real data. So there are some additional applications for it. So this is really exciting, but I would really want to stress that this is not a replacement for data. It's the tool that should be combined and with other methods, and also the data access to the original data set is still important. So why not to use this, or what the challenges are? So for some decisions, it might be actually more appropriate to use original data to make the final decision, in that we might use those synthetically generated data sets to develop methods, or outsource, make it more open and allow wider community to engage and provide various solutions. But ultimately, at the end, we still could use original data set and run the final algorithms or do a final tuning. So that's important. Those methods can be quite computationally and data intensive, especially in some applications I mentioned a moment about generation of a time series data, network data sets. And really, there is a need for tailor-made utility and privacy metrics. So different applications will require different utilities and different privacy considerations. And so this is not a universal solution that will work for all. It's really, there is a work needed and research that still needs to be done to understand what are real opportunities and what are the limitations of this technology. But ultimately, we want to produce the data that is realistic, efficiently, can be computed efficiently, and preserve privacy that we set for it. Couple of challenges, just to give you a couple of examples, the things we are working on at the Turing and in particular in finance and economics program. So like I said, there is a lot of work out there around generation of synthetic data. There is significantly less work when it comes to networks on the time series data. And time series data, it's especially in financial context, the key object that we need to able to synthesize. So the challenge is that it's difficult to capture the dependence in the time dependence in the data. And the other challenge is as we improving privacy guarantees for those generators, the utility drops down. So we need to work we are working on those two challenges. So specifically, a couple of examples of the recent works that came out of our work is the one of the first papers actually that was successfully able to synthesize time series data came from the lab of Michaela van der Schaar from Cambridge, where they combine autoencoders and GANs. And then later on, we've done some work with Nihao and a bunch of excellent PhD students on combining more classical econometrics methods and also bringing some more sophisticated mathematical techniques that improve efficiency of generation of this data. Just a couple of pictures. So this is from the work of Michaela van der Schaar. So here you see comparison of different methods. This is a two-dimensional projection where blue is synthetically generated data and red original data. So you can see that the method A, which is the method they've developed, is doing really well and is really able to produce the data sets that on this metric have high fidelity. And more recently, we've extended that work and demonstrate by bringing, like I said, some mathematical tools to show that the training of those GAN models can be significantly improved. So when training GANs, there is a challenge where we need to solve a difficult optimization min-max problem, and they're really hard to tune. And we've managed to combine this with so-called signature methods that reduce the min-max problem to supervised learning. And through that, we get really good results. Just to show you some pictures. Again, this is where we were trying to synthesize the market data coming from Dow Jones, both prices and volatility. And the blue is historical data, and orange is data that is generated for a model. So you see that the distribution fit quite well. We also look at the various metrics about autocorrelation and correlation, and this synthetically generated data really preserve the statistical properties of original data set for a time series. So going beyond data sharing, like I said, there are many applications of synthetic data generation. And if you think there's many successes, in fact, in machine learning are developed on synthetically generated data. So one of the things that is I want to kind of point everyone to is that recently Financial Conduct Authority actually is working and developing digital sandboxes. And so these are sandboxes with synthetically generated data that allow fintech companies to develop their product and that this hugely increases and helps to promote a competition on the markets. And those digital sandboxes can also be used as a tool for validating algorithms and AI which is being deployed in finance. Those data generators are also a first step towards being able to develop digital twins of economy and various policy simulators. So this is a dream that, for example, Vasco Carvalho was saying yesterday during a session on economics, where we would like to be able to simulate effects of various policies in economy and on the synthetically generated data to make better decisions. But before we are able to do that, we really need to have a good models and for the data, how you bring the different data sets at the granularity that we're interested. There are very exciting applications around AI audit. So Adriano is an expert here. Then those synthetically generated data can be used to validate algorithms and in real time and use under adversarial scenarios. So kind of future-proofing your machine learning pipelines. One of the projects we are working on is around mitigating the impact of bias in the historical data. So here, the idea is that you want to generate a data that is statistically as similar as possible to the historical data, but doesn't suffer from the biases. So if you want to then use on top of that machine learning pipeline, you have a better control on that. So that's quite exciting research. But all of that, and I want to stress that this all challenges are very exciting and that these opportunities are really exciting, but there is really still need for fundamental research. And so that's what we're doing. And the way the future looks is that we will really need to strike the balance between various metrics, develop methods that are fit for purpose, but the future is very bright. Thank you.
Brilliant talk. Thanks, Lucas, for this. I think we're going to have the Q&A session at the end. There's a few questions to be fielded to you. So let me just go to my second speaker. So my second speaker is Steve Roberts. Stephen Roberts is the Royal Academy of Engineering Main Professor of Machine Learning at the University of Oxford. Stephen is a fellow of the Royal Academy of Engineering, the Royal Statistical Society, the IET Institute of Physics. Stephen is director of the Oxford Mann Institute of Quantitative Finance and director of the Oxford Centre for Doctoral Training in Autonomous Intelligent Machines and Systems. Steve, the floor is yours. Thank you.
Thank you very much for the introduction. I'm Steve Roberts, and I'm going to talk a little bit, snapshot of some of our work on AI and machine learning for finance, talk a little bit about some of the successes, highlight a couple of take-home messages that I think have come from this work, but then really follow on to reinforce some of the comments that Lucas mentioned in the previous talk, which are, as I would call, some of the elephants in the room. I think there's no need for me to dwell too much on my second slide, which is the rise of AI and machine learning. This is a slide that comes from a review by Refinitiv at the back end of last year and looks at the enormous, almost exponential rise in the potential revenue worldwide associated with AI and machine learning. And it certainly doesn't seem to be slowing down in finance or anywhere else. So what I'd like to do is take a little bit of a dive down into some of the recent work that we've been doing, really as a snapshot, not just of our work, but also as a vignette of work that's been going on around the world. And that's really the impressive rise of deep hierarchical models. Before I do that, I'd like to present my view of where these kind of things sit in the AI and machine learning spectrum. Let's just get one thing very clear. Deep learning does not sit outside of machine learning. It is a methodology for performing high-dimensional, hyperparametric, very flexible modeling, which enables us to hone in on a bag of functions which have almost arbitrary complexity. It is one of a set of models, including things like hierarchical Bayesian non-parametrics and beyond, which enables us to work with spaces of extremely complex functions that map what we observe in the world to some value function which helps us to solve our problem. This can be seen on the spectrum of a great number of models, all the way from good old-fashioned econometric favorites like multivariate linear models, all the way through things like basis function models, kernel methods, support vector machines, sparse non-parametric models, and beyond, sitting in the middle, right the way through to ultra-complex, high degree of freedom systems, which enable us to bend and twist to the vagaries of the data. A couple of caveats that come with extremely flexible models. One is we are prone to hallucinating structure where there is none, because we have enough flexibility to fit all the nooks and crannies of our data. That's a little bit of a problem that we will flick through as we go through this talk. Secondly, is the perennial problem that on the face of it, it would appear that these models require lots of data. That is not necessarily the case. And I think if we look at the burgeoning rise of probabilistic or Bayesian deep learning over the past few years, this is most certainly a space that we should be sitting in. This means that we can be much more data efficient, given the problems that Lukasz has very elegantly highlighted associated with real data. This is definitely a domain that we should be trying to work in. And there's a lot of benefits for doing that. So by and large, all that I'm going to talk about sits with a crust over it to say, where possible, we try and at least do approximate Bayesian inference. Where are we with all of these kind of problems in finance? And I guess this diagram in some ways is the core of one of my first take-home messages from my commentary. And that is that traditional features in finance, whether they be based on stochastic mathematics like signature methods, whether they be based on traditional econometrics such as delay difference equations and stochastic differential equations, things like Ornstein-Erlenbeck processes, have the problem that these features or representations of our data have come from our understanding of the forwards going stochastic differential systems. They are not necessarily the best ways for an algorithm like a deep learning algorithm to view our financial data. Furthermore, we as human beings understand the ways in which at market data level features that we interpret and understand, things like volume imbalance, volume weighted average prices, various kind of price weighted moves, moving average crossover, and a whole range of time honored methods which we as human beings find really helpful to understand complex markets. These are not necessarily the optimal way of encoding our data for modern AI algorithms. And it turns out we can get a really big boost to our algorithms by ditching these kind of things. So one take-home message from my talk is throw away what appears to be a good feature representation for us as people to understand and allow our algorithms to learn blindly from the raw data that kind of feature representation. Now, one way we can do that is we can recast things like limit order book or market by order data right down at the high frequency level, or even at daily level, things like candlestick plots of kind of open, close, high, low. We can recast those as we see these through time as kind of like a movie of the data and the associated trade volumes. And in this bit of work, what we did is we took this movie and said, this is just a snapshot of what looks like images, and images have structure. And we know from all our friends and colleagues who work in machine vision that the sea change that's taken place in deep learning over the last 5 to 10 years in machine vision is to let the algorithms work right down at the raw pixel level to learn initial low-level representations or filters that correspond to structure in the data, and let that percolate upwards through the hierarchy to learn successively more refined, generalizable pattern upon pattern associated with the structure, the dynamics, and the spatiotemporal structures associated with what bears information in that data. We were really excited that when we did that, we used these kind of approaches that were pioneered by our colleagues in machine vision, that it really improved our results. So the kind of thing that I would sort of highlight at this point, this is a little bit of work from a few years ago, started about 5 years ago, where we have this sort of financial data as an image, including all its volume, coming in as a structured pixelated object, learning filters, learning feature representations at a low level, percolating them up through a deep hierarchical layer system, a deep network, through recurrent layers to learn the dynamics later on. And the second take-home message of my talk is that we often think about learning models as trying to learn to minimize statistical measures within the data. We can show that minimizing a statistical loss function is in many cases never going to maximize your value in the real world. So if your value is a dollar value or something like a Sharpe ratio or some other kind of drawdown moderated reward out there in the real world, train your models to maximize that function, which is your value function that's to do with your problem. Do not try and minimize a statistical value function, because we can show through things like loss calibrated Bayesian theory that the two are not guaranteed to match one another. Minimizing least squares never guaranteed anybody maximum dollar reward. So maximize the thing that you actually care about, and that gives the models an enormous boost. Kind of thing that we find is these work very well compared to baseline. This is really a vignette, not just of our work, but there's been some really excellent work that's been done by other groups, some other people like Ramakant in Oxford, and groups around the world picking up on this and running with it. And I know that this has become very valuable to people. We get a lot of inbound from the finance industry saying, we run your models and with some minor tweaks, they seem to perform pretty darn well. So this actually works not just at an academic level, but actually seems to work out there in the real world. I think one of the exciting things from this framework was that it worked not just out of sample in terms of we train on months of data. We then have a gap and we train on months of data. This is high frequency data. We train on data that's completely out of time sample. In other words, the future of these data sets. But we also, because we've learned these apparent deep generalizations, it appears to transfer. There's a universality to the patterns that are learned in these models. And this is something that we picked up on and has also been picked up with other groups around the world. And you can run assets and portfolios of assets which have never been seen. These are even out of generic asset class. There's an oil and energy company there. Energy companies never appeared in the original training set. So these are stocks that have never been seen by the model before. So somehow these kind of deep hierarchical models looking at the raw market data as pixelated movies, pixelated images as snapshots of the market, are somehow able to learn universal patterns. What's exciting about this is you can actually take pre-trained layers that come from our colleagues who look at patterns in audio and images, and you can apply them to finance data. Structure and informative structure that is non-random patterns appears to be something that is universal across data sets. That means we do not need huge data sets anymore. We can actually pre-learn structure filters from pre-trained layers from audio and from images and a whole range of other things, then bring them across into the world of finance. That means that the beating heart of our models, can be lean and clean and adaptive and work with very small data sets. I think that's a pretty exciting go forward. The second part of the talk I'd like to comment on would be this kind of promise of deep reinforcement learning. What I've just been talking about is we observe a snapshot of the world and we're forced to make a judgment about what we trade right now. We may hold that for some set period, 5 minutes or an hour or a day or a week or even a quarter, but we're still defining the period over which we believe we're going to be making money and taking actions. Inspired by amazing work such as being able to learn how to do things like play Go, I think a lot of people have then said, can we use these techniques to learn policies or strategies whereby our multiple algorithms can trade as agents within a marketplace, playing the game of making money in an adversarial setting against opponents who are trying to make money in the same marketplace. And this is very much about learning game theoretic policies. I always think of this a bit like playing a game of golf where we take shots and we have degrees of belief based on what how good or bad our existing shots have been and how our opponent has played as to what we should now do, and or playing a game. This kind of works. There's a few caveats that I would say about that, and it works very well compared to baseline. Again, what we've done is we've used our representations coming from these deep hierarchical models, and this really does give a pretty big boost. There's a bewildering, there are thousands of papers out there to do with reinforcement learning, and there are enormous dark art tricks of the trade associated with this. So this is an area I'm not going to dwell on, just to say it shows promise, but is very much work in progress. And I think there are some kind of dark art tricks that we should really hone in on and bring this kind of alchemy into the world of mathematics. So let me wrap up by saying I think there are some really important take-home messages that don't require vast amounts of data, that mean we can learn universal patterns in our data. Maybe this is really electricity and fire, as Sundar Pichai says. I think the reality is algorithms are still prone to confusion and failure. This is not a refrigerator filled with food and drink. And as we push in the market to more and more advanced technologies, as Lopez de Prado talks about in his excellent book on machine learning in finance, we need to worry about the kind of things we learn. These are genuine papers. The left-hand one, a little bit tongue-in-cheek about how sunspots, anomalies in finance, politics, the weather, and astrology appears to correlate with financial anomalies. The right-hand one is a genuine article for about 6 weeks ago to do with brain activity of traders, and which foreshadows stock price dynamics. The aggressiveness of traders changes the dynamics of the world around us. It's true. We are at risk always of learning my favorite thing, which is the vomiting camel pattern, which those who've seen my talks before, I absolutely adore. If enough people believe in vomiting camels will vomit. And I think we have a complexity divide between the world of finance on the left and our understanding of how we run these complex multi-agent systems, which at the moment are limited to learning how to pick apples in an orchard where there's just a few agents and playing StarCraft with 20 people. There's a lot of bias. Lucas has picked up on this. The world is awash with this. So the elephants in the room, for me, very little emphasis is ever put on intelligent data ingestion and engineering. We tend to just look at raw market data without thinking that carefully about what it represents. And indeed, is the market data and the way I've portrayed order books even the right way of looking at finance and financial data? Bias Lukash picked up on is absolutely rife, and we must engineer it out. We need to have dynamic systems, and we need to worry obsessively about architecture settings and model choice, because these bias how we look at the world. These are some of the reasons that Gartner estimate 80% failure rate of machine learning, and many quants say we believe in machine learning, but only 25% find value. And this comes from a JP Morgan machine learning conference just around about just over a year ago. So my take-home message, I think the big take-home, really echoes Lukasz's comment. We need to turn the alchemy of AI, which is often pitched very much as a magic solution. It is not. It just fails much of the time. And we need to turn it into mathematics, not magic. I think many of us working as Turing Fellows are trying to work in programs like the Turing Finance and Economics program to say, what is it about even our deep models? What is it about these Bayesian methods in deep models that help us turn the magic of these apparently great solutions into mathematics? And I will leave you there with my favorite vomiting camel, and obviously very happy to take any questions after the following talks. Thank you very much indeed, everybody.
Thank you very much, Steve. As always, highlighting the importance of the gold vomiting camel pattern. It's important to reinforce that. So let me just introduce my last speaker. Is Dr. Vaishak Pal. He's a Chancellor's Fellow and Faculty at the School of Informatics, University of Edinburgh, and Alan Turing Institute Faculty Fellow, a Royal Society University Research Fellow, and a member of the Royal Society of Edinburgh, Young Academy of Scotland. At the University of Edinburgh, he directs a research lab on artificial intelligence, specializing in the unification of symbolic systems and machine learning, with a recent emphasis on explainability and ethics. The floor is yours, Vaishak.
Thank you so much for the introduction. I hope you can hear me. What I'll do for today is not necessarily dwell on any technical results we have had, where we have touched on bias and accountability and whatnot, but I'll mainly speak about some broad work we took on with the NatWest group, where we tried to understand the role that explainability can play in the world of finance. This actually fits in quite nicely with the concluding remarks from Stephen, in the sense that there is a need to pick up these models and use them, but there's obviously some inertia and get them started owing to trust and other concerns about whether you can understand what these models are doing. So in some sense we started off with three very fundamental questions. What's preventing us from scaling machine learning models in the industry? How do we really connect to stakeholder concerns? And again, we have a whole range of stakeholders in the world of finance. Thirdly, which I think is an interesting technical insight, is how do we really navigate the fairly complex space offered by all of these different techniques on explainability? Okay, so if you think about the various stakeholders in any kind of conventional application in finance, it might range from the data scientist who's interested in debugging the model to business owners who want to see the purpose of it. There might be a model risk analyst who wants to understand, is this model safe to deploy? You might have a regulator who's really checking reliability and robustness. And you might have consumers who really care about, how am I being impacted when we move from, say, traditional modeling to something that uses machine learning or deep learning, for instance, right? So these are various stakeholder concerns that we need to take into account that needs to fit in with the overall pipeline of using machine learning. Now, there is this trend, I would say, to think that the only way to get improved performance is by using more and more complex models, a representative example being deep learning. Now, it turns out that this is not really always true. If you have structured data where you have a feature space that is very interpretable, you can indeed get away with simpler models, right? So what complex models allows you, and I think, again, Stephen talked about this, is it gives you the ability to map onto a high dimensional space. So it gives you a lot more flexibility, especially if you have some kind of nonlinear function that you're trying to optimize. Now, having said that, if you do choose a simpler model like a linear regression or logistic regression, you have other problems. For instance, it could be that the feature space is so complex you have such a large linear model that you really cannot make sense of, right? So one way or another, we are in this position where we do want to use potentially better models, but at the same time, we do not want to compromise on our ability to understand what the model is doing. So you might think of this as really trying to optimize performance and explainability to some regard. To give you a very simple example, and at a very abstract level, let's say, for instance, you're thinking of a credit decisioning model where you're trying to look at the probability that a person would default given some feature space, for instance, his income, the amount of mortgages that he might have taken on, et cetera, right? So we're really in the world of what is called as post-hoc explainability. And what we mean here is that we have already deployed a machine learning model. We have tried to engineer the model to be as explainable as possible, but in the end, the model is still very complex, and in which case you need to look into ways to extract and understand what the features in the model and the decision boundaries are really telling you, right? In this kind of avenue, we really care about two questions: is what technique do we really want to apply, and when should we apply them? When does it make sense to apply them? And how do you really navigate, the emerging state-of-the-art approaches in explainability? So what we came up with is a survey paper that you can find a link to on arXiv, and some of the discussion in this slide deck is really reflected in that document. And so what we kind of identified, the take-home message here is that it does make sense to think of explainability as being part of a narrative. Okay, if you think about really a kind of a game between the stakeholder on the one hand and the data scientist on the other, what you're really trying to do is to get to a position where each party understands what their concerns are and finds a way to inspect the model appropriately. Okay, let me give you a very simple example using a series of techniques to kind of get to a point where both the stakeholder and the data scientists are happy, and they're kind of agreeing with each other regarding the fit of the model and its reliability. Going back to this example I have of this abstract example of trying to predict whether a person would default, I've heard from various building societies that one very standard model that's being used is SHAP, right? And SHAP, what SHAP does is it tries to give you a feature relevance for the particular model. And you might see here in this conversation that the data scientist has presented this kind of ordering to the data scientist, to the stakeholder, but the stakeholder raises a concern, right, that this is the time of the COVID pandemic. We might expect people's salaries to decline. So what would really happen to the model? Okay, and this gets us onto a path, a kind of narrative between these two parties. So the first thing the data scientist might try is to consider things like partial dependency plots, where you can really isolate the probability of one variable while fixing all the other ones, okay? And again, the stakeholder gets a bit of an insight, but she's kind of concerned, well, I want to really focus on this one individual, Mr. X, and I want to see what would happen to Mr. X when his salary falls through, or maybe he misses a mortgage payment. We might now think about using something called counterfactuals, where you try to reinterpret the model with respect to a closest data point while changing some of the feature values. Okay, so for instance, if we inspect the machine learning model, we might see that if you decrease the income by 50%, then this loan would be rejected. But if it's just 25%, it would still be approved. Okay. So on and so forth. You can ask various questions and perturb the feature space so as to get the appropriate counterfactual using a technique like this. Let's go further, and let's say, for instance, the stakeholder now actually realizes that the data point for X was kind of an outlier, and is there a way to think about the model with this whole training data removed? Right? So we would use a technique called deletion diagnostics, where you would kind of alter the decision boundary to account for, this point being removed. And so on and so forth. So for instance, there's a technique called INTREES, which tries to look at the model globally and extract certain rules, which you can, pass on to the stakeholder. For instance, it might say that if the income is greater than 20,000 an annum, and this person has not missed any payments, then it's very likely that the loan would be approved, right? So again, as I mentioned, one message we want to take away from this is that although SHAP is very popular, very easy to use, and a whole bunch of banks and building societies are using them, we might want to take a step back and understand that this is not just about looking at the feature space and the relevance of important, which features are important, but rather there is a kind of a more long-standing narrative where you might want to think about how different techniques come together and how they might answer stakeholder questions. I've only listed a few of them here, but there's a whole range of techniques, and each technique is a different way to inspect the model space, okay? So looking at that gives you a way to understand, is this technique relevant for my method and my application, or is it not? This brings me to the last part of the talk, where, again, given that there is a whole range of different techniques, how do we understand them, right? How do we navigate this zoo of different techniques? And we've looked at different taxonomies. Again, you can find the details in the paper, but here are two perspectives I present. There are different taxonomies and classifications by means of which you can place different state-of-the-art methods, and you can kind of understand where do these fit in? What do I need to do with them, right? So what kind of features do they offer? So for instance, there are locally appropriate explanation methods, but there are also global techniques. Which of them is right for my particular application? Which do I need? And navigating these taxonomies and frameworks gives you an insight into how to think about explainability. Another kind of thing that we've also done is try to analyze these different techniques in terms of the advantages and disadvantages. So just to continue on the SHAP thread, for instance, there are two variants of SHAP. There's kernel SHAP and tree SHAP, and both of them have certain assumptions built into them, which might make them appropriate or not appropriate for your particular application. And again, looking at this framework gives you a way to navigate this space. Let me wrap up this talk to kind of say that we have tried to take a bird's eye view of this emerging area of explainability, try to map these concerns to stakeholder questions and to the frameworks. And there are a number of areas we do need to push on, continuing the emphasis from both Lukasz as well as Steve, in the sense that we do need to think about better explanations. We need to understand, for instance, it has been shown that you can come up with adversarial attacks which could confuse the model to think that there isn't bias when there actually is bias, right? So we need to understand, those kinds of issues when we apply these techniques. From our side, in terms of the collaboration and the work we're doing with the NatWest group, we're looking at three avenues in particular. We're looking at the use of causality and how that can be kind of built into certain machine learning models that are being considered. We are looking at how we might be able to cater the explanations, the kind of the extracted, figures and explanations that we get from these models and cater them to stakeholders so that they have a better assessment and understanding of what the model is doing. We are also looking at models that have a more concrete and rigorous notion of inbuilt explainability, where it becomes easier to understand the feature space as well as the decision boundary. That wraps up my talk. I'm happy to take as many questions as I can in the Q&A session.
I guess thanks, Vaishak, for this. Now we are heading to the Q&A session. Let me just, I have the Slido. I have the slide here. Slido app. So feel free to ask some questions. I'm just going to field some questions that I've just came up with myself just to start. And I'll start with Lukasz. The first question is, how do you see the development of synthetic data generation happening in practice? And I think we kind of had some discussions about this previously. Do you think it should be done independently by, let's say, one bank or financial institution, or should it be done by a consortia of institutions and then you have a custodiary somewhere that could have managed that? How do you see that taking place?
Well, I think we are at the beginning of the journey. I I think we are at the experimentation level where we are still learning what those synthetic data generators are good for, and what are their limitations. So there's a couple of ways on to unpack your question. So it is a useful tool that could be in principle developed internally within organizations, and they can use it internally for their own purposes, i.e. sharing data between different departments and so on and so forth. And there is another aspect which I think you're touching upon about more broadly around sharing data for the benefit for the whole, say in this context, financial sector. For example, for applications like anti-money laundering and things like that, we all agree that if there would be a ways for banks to share data, then in principle everyone could benefit. Although using synthetic data in that specific context is particularly challenging. But that aside, so I would see that there would be a benefit of having organizations like either Turing, or there is actually a great initiative in Edinburgh, Global Open Finance Center of Excellence, that could be that middleman of bringing and keeping the synthetic data sets trained in a distributed way from across different financial institutions to provide some more global picture what's happening for the industry for the benefit of whole financial sector. So that would be, I think, the dream direction, and I think we're slowly heading there, but there is still a lot of work to be done.
Excellent. Just a question out to Professor Steve Roberts. The question is, with respect to the, I'm very interested in the difficulties in applying machine learning in finance, and what you have to make a lot of changes in the typical off-the-shelf machine learning tool that you have to apply. What are the key pitfalls or the key challenges you see when you have to make these adaptations in your view?
Yeah, thanks very much for the question. One is worrying about the representation of the original data. That's something that I think is a little unsolved. Secondly is performing meta inference over the model class. I think that that depends very much on the amount of data that you've got. Often we need to have data efficient models which don't need terabytes of data, billions of data points to train with. And that means that we need to do things like AutoML to work out a trade-off between the model complexity, the solution accuracy, and the way in which we are data efficient. The final thing would be the way in which we encode the value function that really matters. As I mentioned in my talk, you don't optimize things in finance by optimizing statistical models, which tends to be off the shelf. So worrying a lot about what your own value function is vitally important. The final thing, probably the best thing I've ever done in finance, is just bring uncertainties in. Finance is a world in which chance and probability reign supreme, and if we fail to be Bayesian, we fail to provide solutions. So for me, it's about making sure we encode uncertainties at every single level.
Yeah, thanks, Steve, for that. There's a few questions now on Slido, and I think I'm going to pick one of those for Vaishak, but also I'm going to add one myself. So one of the questions today in the Slido, I think is becoming quite popular, is when they can find all those references and all those materials. That's the first one. And there's a follow-up question is, how do you see the interplay between and also the interaction with the work that Luke is doing on synthetic data generation? Do you think there's an interesting possibility there for model explanations in your view?
Yeah, so maybe I'll go, I'll do the first one because it's easy. So if you just go on archive.org and search for my name, it should come up, and it's the title of the talk, and all the references are in that document. So it's a fairly long survey paper. I think it's about 30 pages or so, but it has all the references as well as the frameworks to navigate the space to get you started on how to think about different approaches to explainability. Coming to your question, Adriano, yes, there is a very obvious way where Lucas's work would fit. For instance, he does come up with, or he at least considers the various metrics and the measures by means of which the synthetic data is, in some sense, representing the actual data, right? But this is reliant on the modeler being kind of cogent and completely consistent in terms of how the variables on the original data and the synthetic data match up. So you might think about, if you're convinced that you've done a good job, you might think about using some of these techniques to kind of really see, is it the case that both the models are responding in a kind of analogous way, and be convinced that in fact you do have a good representation of the synthetic data, right? The other kind of thing you can do, and I think which maybe Lucas kind of hinted at but didn't expand on, as you recall, towards the end of my talk, I did mention that adversaries is something that you have to care about, especially in the world of finance, because you might not have access to infinite data, right? You have a certain time period. So if you think about that, what you want to do is you might want to guard your model against bias. You might want to guard your model against distribution shift. And there you might want to think about using synthetic data to see if you can make the model more robust, right? That would be another avenue for fitting this in.
Very good. Thanks for that, Vaishak. Now I'm just going to go to Slido, and one of the questions I think is probably for Lucas, even though I think also applies to Stephen. Most popular question is, if the data is good enough to generate synthetic data, isn't it good enough to train a predictive model? That's an interesting question, which I think is, what is the benefits of using synthetic data generation beyond just training a predictive model?
Well, like I said, one functionality of that tool is data sharing, i.e. that there might be, if the data is private, there might be a very small number of people that will have access to it. Whereas if you can extract relevant sample with that captures the main statistical properties of the data for the task at hand, then you can open it up. For example, you can run some sort of a competition style in the Turing. What we do is that is data study weeks where we bring together 20, 30 PhD students and young researchers working on specific challenges, and being able to use data, synthetic data, could unlock and help to develop new ideas. That's one part. This data sharing, in my view, and I'll touch upon what just Vaishak said and what Stephen said about this uncertainty and robustness. I think this is absolutely critical. In fact, for majority of the applications of machine learning in finance, you don't want to generalize well to historical data. So the kind of a generalization question is about, you train a model on some sample of data and you want it to perform of independent sample, assuming that this will come from the same distribution. That will never happen in finance. The world is moving forward, and new data arrives, and there was inevitably, there will be a distribution shifts and changes in the distribution. So you want to have that inbuilt robustness, or you want to control uncertainty in your predictions. And so using synthetic data is one way to achieve that. The other ways, of course, where you can do perturbation to the future scenarios or generate scenarios that you haven't observed in the historical data and see how your model performs. And, for example, in the question of explainability, you definitely want to do that, something like this. If you use some explainability tool to unpack a model or provide some information about your black box model, you want to make sure that this is robust. That the small change in the data of input data will not lead to significant change of the explanation, because that would mean that the explanation wasn't very good to begin with. So plenty of so that is additional benefits that you can do. And the final one is the for people working on machine learning and on this big neural network models, there's a question more fundamental question, do we really believe that we found now the methods that allow us to be the curse of dimensionality? The curse of dimensionality is a term that has been coined by Richard Bellman when working on optimization, dynamic optimization. And that means essentially that as we want to bring more data or look at the bigger models and bigger problems, then the computational cost of processing all of that information grows exponentially. So I think conjecture is that those sophisticated machine learning tools are extremely good in identifying lower dimensional representations that would be very difficult to handcraft. And so using synthetic data gives you a chance to be able to discover some of those lower dimensional representations. There's many different applications, but like I said, this all requires research and specific and can be properly answered within, you know, when having a specific questions in mind.
Thanks, Lucas. There's a lot of questions with respect to CNNs and other techniques for Steve. And what really impresses me about these questions is that it feels like, as Steve pointed out, is the dawn of a new age for machine learning, AI, and so many data scientists are now being employed by banks, and you have all AI labs in several banks, etc. There's really a new wave coming. But at the same time, it feels like there is a twilight for the physicists with the whole quant, etc., kind of going down. How do you see that actually evolve, Stevie, in your view?
I don't see that, and I should say I'm a physicist by training. Everything that I do is motivated by the fact that learning is just really applied 19th century physics. It's all about doing work on a system to reduce entropy. Our deepest understanding of how things like deep learning work come from thermodynamic physics representations of what these hierarchies are actually doing. I think it's a profound underpinning science. And my kind of take-home comment on this is, if AI runs the risk of stopping being a science, and if we allow it to not be scientific, so that every single model, every pre-processing step, every layer that we introduce in our solution makes tacit assumptions about the nature of the data and the nature of the properties of what it is doing. If we fail to be scientific in the way we experiment and build these things together, then we've lost it, and we don't have robust, reliable AI. So again, this comes back to turning alchemy into mathematics, or maybe I should say into just good science. AI needs to be a science discipline, not just it works, that's the end of the story. I'm sure nobody would disagree with that, but we do need robustness and reliability, and that requires scientific principles in the way we choose our models, train them, work with our data and beyond. So for me, scientists are at the core of everything that we should be doing in the AI space.
I think amazing answer. I couldn't agree more. It feels like sometimes we just think that a data-driven approach is the way forward, and we forget about the whole first basic principles, right? When we're doing things. And now to Vaishak, there's a question for you, which is: can you define what an interpretable model is? Is it that there is a solid theory behind it? For example, null boundaries. Is a Gaussian process interpretable, etc.?
Right. That's kind of a very open-ended area to get into. So, of course, interpretability is not precisely defined, and that's one of the issues with this area. But what we do understand, in some sense, the reason that this is so open-ended is because if you think about how explanations work between human beings, there is already quite a bit of mystery about it. So in terms of what the interlocutors are saying, what is being interpreted, and what is the reason for even giving an explanation. So there's a whole bunch of questions you can raise from even psychology and social sciences. So coming back to the specific a point this person raised about Gaussian processes and whatnot. So in some sense, right, the quest here is to, of course, we want to define it precisely, but at the end, what we are the first step we're taking is to understand what exactly is the model's decision boundary looking like? How sensitive is it? What is the connection between the decision boundary and the training data? How do we perturb this decision boundary if we have incorrect training data, or if, for instance, there are adversaries and so on and so forth? So to that extent, I feel like it is interpretability is turning into some kind of functional mapping from this machine learning model to a space where we can inspect and scrutinize what the model does. It's not a very satisfying answer from a mathematician's point of view, but it's the one we have. That's not, and taking steps forward is trying to again make it precise what exactly is the range of stakeholder questions to which we can map this function to, right? In some sense, it turns out that by changing the stakeholder questions, you want to inspect radically different aspects of the model. So, we are scrutinizing the model. We understand the mathematics behind the scrutinization, but the question is this level of scrutiny that we're applying tied up quite nicely to the stakeholder question? So there is a mapping, challenge there that we need to work out.
Yeah, I think you covered quite a good ground, Bashak, with your answer.
Can I add to this?
Yeah,
because it's a little bit also philosophical question. I want to actually reinforce what just Stephen said about physics. So we need to think a little bit how we were building models before, AI excitement. And actually physics is the subject we should be looking into. So, you can think of, you will look into data and then you will try to understand what's going on, and then you will propose the model. And typically the thinking was that the model should be as simple as possible, but not simpler. and then you will evaluate it on the data, and maybe you will go back to the drawing board and improve your model or change certain things. And through that process, effectively, you were gaining understanding, very good understanding of the model, because what works, what didn't, what captures reality. And so this is this era that I would call parsimonious models, which we all learn on, one-on-one statistics. With this machine learning, deep learning models, over parameterized models, the philosophy is a little bit different. You're not sure what the model is. So you say, let's start with this big set, big bag of all possible models, and let me just try to find one of many that fits the data. This is not quite a modeling approach. Then, of course, leads to all the questions about lack of explainability, that we're not sure what's going on, and that is post hoc additional methods that allow to inspect the model, which I think is very exciting, interesting area. But we just need to think that what's a model fitting a data is not building a model, and I think it's important to differentiate, which of course also
if I can add one quick point to that, and it's something Stephen raised as well. In some sense, I mean, if you ignore deep learning for now, but you even take something like support vector machines, right? This has a very rigorous mathematical backing. It's a very celebrated technique, but in some sense, the way support vector machines work is that they move the data space to a kind of a very high dimensional hyperspace. So if you do this by using kernels and whatnot, the trouble here is that even at this level, even though the mathematics of the model is clear, we do not seem to understand what this decision boundary really does. Right. So again, the approach here is that if you look at the way support vector machines have gone through the ages, people have been adapting and tying up the data to the model. For instance, if you were training language models, if you were training, I don't know, grammars, what kind of changes do you need, right? So people have been trying to map that out, but absolutely essential is to think about what exactly are we trying to do here, right? What is the purpose of this training, and what exactly do we expect to inspect when we do train this model? So I would say that, even though the foundations of the model is central, there is a skew in terms of how these models have been applied. People have taken the approach, I have this model, it's a good model. And again, the model is used very in this kind of abstract sense, not necessarily tied to the task at hand. but in the sense of this is an approach, a black box function, where I passed up some data in and I get some output out. And I think that is leading to all of the problems we're having right now, because we have not really mapped on the task-specific generalization and property-based approaches to these models. And a tighter linking of this, I think, could help us, better relate the problem we're trying to solve and get more accurate predictions, essentially.
Yeah, and I think I just want to go back to Steve's point is about first principles. Going back to that, and I would like to even to get Steve in the conversation with respect to the uncertainty, with respect to the Bayesian approach, which I think is quite informative, and it goes back to the point that you made in your talk about maybe we don't need that massive amount of data. Maybe just modest amount of data with a good prior, we can make meaningful predictions. Can you explore a little bit more, Steve, about this?
Yeah, let me say, it's about having models whose outcomes are honest and humble. If you give me very little data, my outcome variables will be extremely uncertain. And that means that if you take action upon those outcomes, there is an inherent risk, because my model is clearly defining itself to be very uncertain associated with what it believes will happen, or whether that action is the right one to take. There is an enormous difference then. So then we move on to kind of classical statistical consequences and loss. That loss is something which potential downside scales with my uncertainty. So if I have a model, even if it's right, but my error bars, my uncertainty in a decision or a forecast is very, very large, I may want to avoid taking an action at that point. Now, what we know from work not only we have done, but many other groups as well, is that if we veto making trade actions in a finance system according to degrees of uncertainty as put forward by the model, and we must have these very honest models that say, this is my guess, but I don't really know. In cases where that model says, this is now within kind of the top 1% of my confidence, we end up with provably better value coming out of those models. So small amounts of data is small knowledge. Don't think big data, think big knowledge. You can get big knowledge from small data. You can get small knowledge from big data. It's the amount of information entropy. It's about the amount of potential in that data to decrease your ignorance about the things you care about in your solution space. And you only give me a small amount of data, I may not be able to produce a refined enough solution, but at least my models should be honest to reflect their own ignorance. So my plea going forwards, and again, I think it just ties into the science comment, is models need to declare their degrees of ignorance. Beautiful things come from that. One, we've done a lot of work recently on adversarial robustness. Models that do this are way more adversarially robust. They don't get spoofed. Secondly, in coming back to Vaishak's excellent comments about things like the credit decision problem, you can go back into these models and say, if I could just do one thing, if I could change something, learn something new about the world, or get you to modify your behavior or capture some more data from out there around me, what would that be in order to refine my degree of uncertainty to a point where maybe your credit rating would drop across a boundary? And we can, in a profound way, we can address these kind of questions. So I think the question would be, what's there not to love about these? What's there not to love is they're painful computationally. And I think if we need to do things properly, it just requires us to take that pain and know that in 5 years we'll have machines that are big enough for us to do all this. Hence the revolution in everybody doing things like Bayesian deep learning in the last few years.
Yeah, I think on this last note, I should just have to thank my speakers. Thanks, Lucas Bruch, Ashok Belli, and Steve Roberts for your amazing insights. And thanks for AIUK for organizing this session. Thank you all very much, and I guess see you all soon, and looking forward for the next sessions.